All right, this is assignment number 13. This is a long assignment, so hopefully you got a decent portion of it finished in class, but feel free to come into office hours too if you want to finish up or get help. All right, first one, we're doing just number 1 in this section. So assume that x and y are both differentiable functions of t and find the required values of dy dt and dx dt. So here's our equation. Y equals, I'm going to think of this as x to the 1/2. For part A, we want to find dy dt when x equals 4. So we have this y equals x to the 1/2. We're going to take their derivative with respect to t of both sides. And remember, this whole section is basically about chain rule. So because you're taking the derivative with respect to t of expressions that have variables that are not t, you need to use the chain rule. So the derivative of y is 1, and then we're going to have times dy dt. The derivative of x to the 1/2 is 1/2 x to the negative 1/2, and then we need chain rule dx dt. All right, so right here, find dy dt when x equals 4. So, and remember, we also know, well, I guess this doesn't matter, but if we needed to know the y value, we know y when x equals 4 because we have this equation we could plug into. So I don't know dy dt. Oh, actually, sorry, let me put this over here. So I want to evaluate dy dt when x equals 4. So I'm just going to plug in what I know. So that's equal to 1 over 2 x to the negative 1/2. I'm putting a radical down here, radical 4. And then what's dx dt? It says dx dt is 3, so times 3. That's 3 over 2 times 2, so 3/4. You don't have to simplify anything really on the AP Calculus exam. Stuff like this I do simplify, but you'll see in some of these problems where the answers are more complicated, I'm doing them no calculator, but I'm not really simplifying much. Part B says find dx dt when x equals 25, and now we're given dy dt equals 2. So I'm using the same equation, I'm just subbing in different numbers. So 2 is dy dt, that's equal to 1 over 2 radical x is 25, and then it's times dx dt. So this is 1 over 2 times 5, so this is 1/10 times dx dt. To get rid of 1/10, I will multiply by 10 over 1, so 20 equals dx dt. Remember, the related rates problems are just putting words to this skill. Eventually, you'll just be taking the derivative with respect to t of an equation and plugging some numbers in. For number 5, we're doing A and B. A point is moving along the graph of the given function such that dx dt is 2 centimeters per second. Find dy dt at the given values of x. So we have this equation for y. We're going to take the derivative with respect to t of both sides of the equation. And I keep writing this out just because I think it's a good habit to get into to tell your brain what you're doing instead of just diving right into the derivative. So this derivative is 1 times dy dt. The derivative of 2x squared plus 1 is 4x dx dt. 4x plus 0, technically, dx dt. And then remember, we know dx dt is 2 for these two problems, and x equals negative 1. So dy dt evaluated when x equals negative 1 is equal to 4 times negative 1 times 2. And so that's equal to negative 8. I'm going to put a label on this because dx dt is centimeters per second. A lot of times for our free response problems, we will be asked to find a value and include units in our answer, so that's a separate point. All right, for x equals 0, it's the same equation, you're just subbing different information in. So dy dt, I don't have to take the derivative all over again. It will be 4 times 0 times 2, which is just 0 centimeters per second. All right, for number 16, the radius of a sphere is increasing at a rate of 3 inches per minute. Part A says find the rates of change of the volume when R equals 9 and R equals 36. So what do we know? They gave me the rates of a radius. So dr dt is equal to 3, and it's increasing, so positive, 3 inches per minute. And they're asking me for part A to find the rate of change of the volume, so dv dt, when R equals 9 and 36. Do that in two different things. And so I'm going to use the volume equation for a sphere. They will give you these formulas on the AP test, and I will give them to you on your chapter test or quiz or whatever. So the volume of a sphere is 4/3 pi r cubed. Okay? And I want to take the derivative with respect to t of both sides of this equation. Again, you can skip the step of writing it out if you want to, but I think I have found that it helps me more clearly understand what I'm doing in this process. So when I take the derivative with respect to t, I get dv dt equals, this becomes 4/3 pi times 3r squared. So 4/3 times 3 is just 4 pi r squared. And remember chain rule, because this was the derivative with respect to t, dr dt. And then we want to sub in what we know. We're trying to find dv dt when r equals, let's start with r equals 9. So that's going to equal 4 times pi times 9 squared times dr dt, and that was given to us as 3. Again, you don't really have to simplify this. You can just leave it like that, and I'm going to say it's volume. So I'm going to say cubic inches per minute. I might have simplified it on my answer key, but it's not required. And then we're also supposed to find this for 36 inches. So dv dt when r equals 36 is equal to 4 pi times 36 squared. I'm not going to figure out what that is, times 3. And that again would be cubic inches per minute. All right, for part B, sorry, hold on a minute. Okay, for part B, explain why the rate of change of the volume of the sphere is not constant, even though dr dt is constant. So dr dt is increasing, the radius of the balloon is increasing at the same rate, no matter what the volume is, no matter what the radius is. But what is that doing to a balloon? So just picture in your mind a balloon blowing up from empty to filled. When you first start, it expands pretty fast, right? And then as it's getting bigger and bigger and bigger, the size of the balloon looks like it's increasing a lot more slowly. So just logically, this makes sense to me. But we can go back to, what was the equation for dv dt before we plugged anything into it? It was this. So it was equal to 4 pi r squared. And even though dr dt was constantly 3, this is an equation with a variable in it. dv dt is dependent on what r is. If it were just 4 pi times 3, it would be constant. But dv dt has a variable of r in it. So dv dt is, I'm going to say dependent on, it's the dependent variable, dependent on the variable r. So not constant. It's not a constant function. It's a quadratic function, in fact, for this one. All right. For number 17, a spherical balloon is inflated with gas at the rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing at the instant the radius is 30 and 60 centimeters? All right, so what do we know? We know this time the volume, dv dt, the rate at which the volume is changing, I should say. It's inflated, so this is positive, 800 cubic centimeters per minute. They're asking me to find dr dt, how fast is the radius changing? when R equals 30 and then 60 centimeters. And what should I be using? Again, you'll be provided the volume of cylinders, cones, and spheres. So in the problem as needed. And so volume is equal to 4 pi over 3 r cubed. All right, so I'm going to take the derivative with respect to t of both sides of this equation. It's okay if I'm going to keep doing it throughout the assignment, but you can start skipping that step if you're comfortable with it and getting right to my next step, which is what was the derivative equation. So I'm just going to write this as dv dt. 4/3 pi times 3r squared becomes 4 pi r squared. Chain rule, dr dt. And then we plug in what we know. So this time we know that the volume is increasing at 800 cubic centimeters per minute, and that's equal to 4 pi times, in this case, 30 squared times dr dt. That's our unknown. And again, you do not have to simplify, so I might just leave this ugly. 800 divided by 4 pi times 30 squared. I know that's a bit frustrating. Well, not frustrating, but like we have been harping on being able to simplify. And maybe if I had to do something else with this, I would simplify it. But if this is just my final answer, the AP test does not require you to simplify. So then what about for part B? The only thing that changes is the value of R. So I'm just going to say, okay, then dr dt would be equal to 800 over 4 pi times 60 squared. All right, number 21. At a sand and gravel plant, sand is falling off a conveyor and onto a conical pile at a rate of 10 cubic feet per minute. The diameter of the base of the cone is approximately 3 times the altitude. So I need to draw this. Here's my cone. The diameter, I'm going to make that 2r, is equal to 3 times the altitude, but I'm going to call that height. I just want to establish that. The diameter, the reason I'm making it 2r is because volume of a cone is based on r, so I don't want to have d in there. All right. And what does it say? At what rate is the height of the pile changing when the pile is 15 feet high? So let's go through what we know. What did they give me? 10 cubic feet per minute. So I know dv dt, and we're piling up on this, so it's positive 10 cubic feet per minute. What do they want me to find? At what rate is the height of the pile? So find dh dt when h is equal to 15 feet. All right. And before I dive right into my equation, let me start with the equation. They will give you the formula for volume of a cone. It's 1/3 pi r squared. Pi r squared is the shape of the base, right? Circle. Times h. And it's a third. I kind of think of this as like, I don't know, is it a third of a cylinder? Because a cylinder is just pi r squared h. So think of a cone as a third of a cylinder, I suppose. I don't know if that's completely accurate or not. I guess it seems like it. Okay, anyway. I do not want to dt both sides right now because I have two variables and I have no information about dr dt. And if I correctly take the derivative of this, I would have a dr dt because I'm doing product rule. So instead, I need to rewrite this volume as just a function of h because I only have variables dv and dh in this problem. So back here, let's go ahead and solve this for r so that we can use substitution and replace the r with something in terms of h. All right, so volume is, let's just make this pi over 3 instead of 1/3 pi. Instead of r squared, it's 3h over 2 is getting squared, and we're multiplying by h. So let's clean that up. This becomes 9h squared times h. So 9 pi h to the third over 6. And I should reduce the 9 over 6. So volume is 3 pi h to the third over 2. Over 4. Sorry. It's not 3 times 2. It's 3 times 4, which is 12. And yeah, 9 over 12 is 3 over 4. There we go. All right, so the next thing is to take the derivative with respect to both sides. Hold on. Sorry. Okay, so now we need to take the derivative with respect to both sides of t. Said that backwards. You know what I mean. Derivative with respect to t of both sides. Sorry. It's May. I'm trying to coordinate plans for one of my kids while making a video. So anyway, okay. This is dv dt. This is going to become, let's see, 9 pi over 4 times h squared. And remember dh dt, because we just took the derivative of a variable of h, but it was supposed to be with respect to t, so chain rule. And then plug in what we know. So we were given that dv dt is 10, and that's equal to 9 pi over 4 times h is 15, so 15 squared times dh dt. Bring this up here a bit. And so again, you don't really have to simplify. You can just say, all right, multiply by the reciprocal of this. So I'm going to make it 40, 4 times 10 over 9 pi times 15 squared. And yeah, you don't have to simplify things. You can, certainly, but I'm not going to. So that's equal to dh dt. Oh, and I do need to put a label on this. Height is a linear measurement, so it should be feet per minute. All right, for number 24, a trough is 12 feet long and 3 feet across. See this figure? 12 feet long, 3 feet across. And its ends are isosceles triangles with altitudes of 3 feet. Now, when they say altitudes, I want to coordinate that to the picture. That's the height, right? The depth of this water would be the altitude of whatever triangle we're looking at. So if water is being pumped into the trough at 2 cubic feet per minute, how fast is the water level rising? What is the water level when the depth of H is 1 foot? So water level in this case, we're looking at dH/dt, trying to find dH/dt, because the water level, how deep is the water? That's the same as dH/dt. All right, so for part A, we know that, where'd it go? dV dt is equal to 2 cubic feet per minute. Positive because water is being pumped into this, so the volume is increasing. They want me to find dH dt, and that is when H equals 1. Oh, I don't have to write it like that, sorry. When H equals 1 foot. And what am I going to use? So any prism has a volume of the area of its base. So the area of its base is technically the isosceles triangle, the two parallel sides, faces, I should say. So it's the area of an isosceles triangle and times the length of that prism, which is fixed at 12 feet. So what about the area of an isosceles triangle? Let's see. So let's puzzle this out here. We have this triangle. Now, why am I drawing it upside down like that? Okay, so sorry. This base is changing, right? We know that I'm going to call this the base, call this the height, which is h. The area, over here is 1/2 base times height. And let's see, we're looking at a base of, are we looking at a base at the highest part where the highest mark is? B equals 3, and we also know that the depth is 3. H equals 3. And so what that means is B compared to H is 3 over 3. So that just means that B equals H. So in my formula, when I'm doing volume of this prism is going to be the area of the triangle. So I could start out like this. Okay, it's 1/2 base times height, and then you multiply that face times the depth, which is 12. But we just said B is equal to H. So we could actually just say, all right, 1/2 of 12 is 6. Instead of B times H, it could just be H squared. I want to get rid of the B because we're looking for dH dt, not dB dt. All right, so V is equal to 6H squared. And we can now take the derivative with respect to t. So dV dt is equal to 12H dH dt. I skipped right to finding those values. We know dV dt is 2. We're looking for when the height is 1. What's dH dt? So if I divide by 12, I will simplify that. That's 1/6. And this is measured in, it'd be feet per minute. All right. So when you have a cone or something triangular like this, where the base and the height would be changing together, you can look at the full size of the shape and compare that base to that height, and your base and height should be changing at that same rate throughout. Okay, so for part B, if the water is rising at a rate of 3/8 inches per minute. I have to be careful here. Inches per minute. I wonder if I might not have caught that on my. Did I catch that on my answer key? I might not have. Okay, I'm going to point that out now. So this is dH dt is equal to 3/8 inch per minute. But everything's been measured in feet so far, so let's take a look. When H is 2, now H is 2, remember H is originally measured in feet. So really this is what I know. I want to find the rate at which water is being pumped into the trough. So I want to find dV dt, but I'm going to find it in cubic inches per minute. So I don't think, it doesn't, see, this is kind of annoying that they didn't specify a unit here. So I'm going to assume that's 2 feet. So I'm going to say H equals 24 inches instead of 2 feet. So I did not do that on my answer key. I'm sure if I check the back of the book, obviously one will be right, one will be wrong. So we'll just see. All right, and then I'm going to use the same formula I had here. So I'm going back to V equals 6H squared. And so dV dt will equal 12H dH dt. And this time I don't know dV dt, but this would be 12 times H. So I'm going to put in 24. And then dH dt is 3/8. So let's just simplify this a little bit, just because sometimes it bothers me not to. 24 over 8 is 3. 9 times 12, let's see, 10 times 12 is 120. And so 9 times 12 is just, should just be if I subtract 12 from that, right? I don't know. I always screw this up. So if I subtract 12 from that, what do I get? 108. Does that seem right? I think so. All right, so dV dt is equal to, 108. And that would be cubic inches per minute. So if I remember to update my answer key, I will do that. If not, maybe we'll have something to talk about in class. All right, moving a ladder. A ladder 25 feet long is leaning against the wall of a house. I forgot to snip the picture in here, so I think I can draw a ladder leaning against a house. Let's see. Here's a ladder, 25 feet. All right. And the base of the ladder is pulled away from the wall at a rate of 2 feet per second. So here's the base of the ladder. It's heading this way, which means the top would have to be sliding down. I like to call horizontal distances x and vertical distances y as much as I can. And let's just see what we have here. So that means that I know dx dt is equal to 2 feet per second. And I know that it's positive because x, this distance from where the base of the ladder is to the wall, that distance is increasing as it slides away from the wall. They're asking me to find for part A, how fast is the top of the ladder moving? So that's going to be changing y's distance. So find dy dt when x equals 7, 15, and 24. And what am I going to use? Of course, I'm going to use x squared plus y squared equals 25 squared. Now, when I take the derivative of this, I'm going to need to know not only values of x, but values of y. So hopefully you remember your Pythagorean triples back from your geometry days. If not, you get to do Pythagorean theorem. But 7, 24, 25 is a Pythagorean triple. I shouldn't put, these look like minus signs. Sorry, 7, 24, 25. So if this is x, this is y. If we have a 15 there, if x is 15 and the hypotenuse is 25, that's probably a scaled up 3, 4, 5, right? 25, 15, what is y going to be? So remember, you can reduce this to a similar triangle. You can say, well, that would be if I divide by 5, hypotenuse of 5, leg of 3, this one's got to be 4, scale it back up here, multiply by 5 to get back here, that's 20. So when x is 15, y is 20. And then the last one is just if x is 24, then y is 7, and hypotenuse is still 25. All right, so I'm going to use that. So when x is 7, I'm going to take the derivative with respect to t of both sides. So I get 2x, actually maybe I'll put that up here. 2x dx dt plus 2y dy dt. The derivative with respect to t of a constant is 0. We can divide by 2. Okay, and then plug in what we need. So when x is 7, so we have 7 times dx dt, which we were given to be 2, plus y is 24 when x is 7. Don't know dy dt. Solve for dy dt. dy dt when x equals 7 is equal to negative 14 over 24. Of course, you can simplify that to negative 7/12. Not required. But when it's easy like that, I like to do it. What about when x is 15? So remember, you can't use your scaled down 3, 4, 5. You had to scale it back up. This is the size triangle. Use the same formula, though. So now it's 15 for x. dx dt is still 2. Plus y was 20. Dy dt equals 0. So dy dt when x equals 15 is equal to negative 30 over 20, which is negative 3 over 2. And our last one, what about when x is 24? So 24 goes in for x. dx dt is still 2. Y is now 7. Don't know dy dt. This is 48. So dy dt when x equals 24 is equal to negative 48 divided by 7. And oops, I should have labels on those. Feet per second, feet per second, feet per second. Those are all uh, linear measurements that are changing at a certain rate. Okay, for part B, consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So we still know, I should say, dx dt is equal to 2 feet per second. They're asking me to find the area, so I'm going to call it dA dt when x equals 7. And remember, we know that also means y is 24. Probably need that. And what is area of a triangle? It's 1/2 its base times its height. So the area here, I'm going to use area equals 1/2 base times, not base times height though, x times y. And then I'm going to take the derivative with respect to t. So I'm going to group this together, both like the 1/2 x, I'm going to call that my first function. So it's first times derivative of the second plus second times derivative of the first. You can go out of order with that. Some people like 1 prime times 2 plus 2 prime times 1. Some people do it that way. This is just the way I learned it. And then we can plug everything in now. So remember, we also actually know that dy dt, we just found this from part A. It's equal to, what was it when x was 7, dy dt was negative 7/12. I'm going to need that from part A. All right, because I needed something to fill in here. So dA dt is equal to 1/2 times 7 times negative 7/12 plus y, which is 24, times 1/2 times 2. Again, you don't have to simplify this. I'll do a little bit here. This is negative 49/24 plus 2 times 1/2 is 1, so plus 24. That whole thing would be square feet per second. All right, for part C, find the rate at which the angle between the ladder and the wall of the house, so be careful with this, the ladder and the wall of the house, so this angle here, it matters where you put theta. Find the rate at which that angle is changing when the base of the ladder is 7 feet from the wall. Okay, so I still know that dx dt is equal to 2 feet per second. And just because I may or may not need it, dy dt, remember, was negative 7/12. And they're asking me to find, this time it's an angle, so let's call it d theta dt when x equals 7. And remember, that's also, we know y is 24. And I need to use, so you can use any trig equation here. It's traditional to use tangent, but if we think about this, why use tangent when tangent would be x over y, and I'd have to do quotient rule with that, versus using sine or cosine where the opposite over hypotenuse or adjacent over hypotenuse, you only have one variable there. So that's just a really easy power rule there. So I'm going to use sine. And again, it doesn't matter, but I've got lots of choices here. I want to use sine because let's set up that equation. Sine theta is opposite of the angle at that top there is x, and the hypotenuse is 25. So I want to use this simply because dx dt is 2. I would rather work with plugging in 2 than plugging in negative 7/12. But it does not matter, and you don't have to simplify much. So it really doesn't matter. Like, pick your favorite trig equation. And then take the derivative with respect to t of both sides. All right, so the derivative of sine is cosine theta. d theta dt. And the derivative of x over 25 is just 1 over 25. And then this would be dx dt. Now, you might not have a calculator for a problem like this, and whether you have one or not, you do not need to find theta to then find cosine theta. Remember, all you need to find the exact value of cosine theta are the sides of the triangle. And this is a 7, 24, 25 triangle. So what is the cosine of theta? It's right there. It's 24 over 25. I do not need to know how many radians theta is to figure that out. All right, and then this is 1/25 times, remember dx dt was just 2. So solve for d theta dt. It's equal to 2 over 25 times the reciprocal of this, 25 over 24. And I'll simplify this since it does so nicely. D theta dt is equal to 1 over 12. Theta is always measured in radians, so radians per second for this one. All right. Number 26. A construction worker pulls a 5-meter plank up the side of a building under construction by means of a rope tied to one end of the plank. Assume the opposite end of the plank follows a path perpendicular to the wall of the building, and the worker pulls the rope at a rate of 0.15 meters per second. How fast is the end of the plank sliding along the ground when it is 2.5 meters from the wall of the building? That's a lot of information. Let me put in some variables here. So I'm going to ignore what somebody wrote in here. I'm going to make the vertical distance y and the horizontal distance x again. And the rope is being pulled up at this rate. So what I know is dy dt, you know the vertical rate, and that's equal to 0.15 meters per second. They're asking me to find the rate at which the bottom of the plank is sliding this way. So they want me to find dx dt when it's 2.5 meters from the wall. So that's the horizontal distance again, when x is 2.5 meters. And what will I use? Pythagorean theorem again. So x squared plus y squared equals 5 squared, which is 25. So if I take the derivative with respect to t of both sides, it's not really proper notation there, whatever. So this is 2x dx dt plus 2y dy dt equals derivative of a constant is 0. Let's get rid of those 2's. I like to rewrite the problem because I find if I don't, sometimes I accidentally include the 2 in one part when I canceled it somewhere else. That messes up the math. Okay, and now plug in what we know. So x is, now remember, if we know x, we also know y. So let me do that math off to the side. X is 2.5 or 5 over 2. I'm going to operate as if this is, let's pretend we don't have a calculator. So x squared plus y squared equals 25. So y squared is equal to 25 minus 25 over 4. That's mathable. This is 100 over 4. So y squared is 75 over 4. Square root that. No plus or minus. We're talking about distances here. So this would be like 5 radical 3 over 2. It is important if you are using a calculator that if you did a calculator to find y, that you do not round your answer for y, because it will throw off your final answer and you won't get credit for it. Excuse me. So I'm going to say y is 5 radical 3 over 2. And then I'm going to plug in what I know. So 5 over 2 times dx dt, we don't know, plus 5 radical 3 over 2 times 0.15, let's say 15/100ths, and then reduce that. Divide by 5. That's 3/20ths. Again, you don't have to simplify. You could have decimals and fractions and whatever, but a little bit of me wants to simplify this a bit. 5 over 20 is 1/4. Okay, so get dx dt by itself. Subtract 3 radical 3 over 8. I simplified the 5 over 20. Did a bit of math there. Multiply by 2 over 5 to get rid of that guy. 2 over 8 is 1 over 4. Even though we don't have to simplify stuff, it is in your best interest to be able to simplify and cross cancel instead of it's important to know when you can cancel like this and when you can't. So if it's just we're multiplying a bunch of fractions together, it's best to reduce or divide before you multiply. So that's negative 3 radical 3 over 20. It makes sense this is negative because x's distance, as we slide this board up, it's getting closer to the wall, so x's length is decreasing. That's measured in meters per second. That was all that question asked. Okay. 28. Now this one, I think this is the hardest question with like the speed thing that they're asking me about. So a boat is pulled into a dock by means of a winch 12 feet above the deck of the boat. So 12 is fixed. This is the Y value no matter what. What's changing is I'm going to keep with the C that someone wrote in here, C for a hypotenuse, and I'll keep this horizontal distance as X. So the winch pulls in rope at a rate of 4 feet per second. Now, this question is asking about speed. I think maybe in my answer key I might have included like a negative because if we're pulling this rope in, the length of the rope, which I guess is C here, it's getting smaller, but they're asking about speed, which just means like ignore the negatives. That's all they're trying to get at. So I'm going to say dc dt is equal to 4 feet per second. What's the speed of the boat? So the speed of the boat, sorry, this is what I know. What they're asking me to find is the speed of the boat. Well, the boat is traveling on this horizontal path here, so that's dx dt. When there are 13 feet of rope out, so when c equals 13 feet. And what do we know? Remember, we're probably going to need to know x. What is x when this is 13? This is another triple, 5, 12, 13. X equals 5. And then follow-up question, what happens to the speed of the boat as it gets closer to the dock? So we'll deal with that in a second. But what do I need to use here? So use Pythagorean theorem again. X squared plus 12 squared equals c squared. Take the derivative with respect to t, of both sides. So this becomes 2x dx dt plus 0 equals 2c dc dt. All right, and then we can get rid of the 2's. Clean this up a bit, get rid of the 0. X times dx dt is equal to c times dc dt. Let's plug in what we know. Find dx dt. So x is 5. We don't know dx dt. C is 13. dc dt is 4. And solve for dx dt. So what is this? This is 4 times 13 is 52 over 5. That will be measured in feet per second. So that's the speed of the boat at that instant. And then it says, what happens to the speed of the boat as it gets closer to the dock? So again, I'm thinking about this and like, imagine this motion. You start pulling in a heavy object. It starts off pretty slow, but as it gains momentum, it starts speeding up, right? So I'm expecting my answer to be like, oh yeah, the speed of the boat is going to increase as it gets closer to the dock. How do I show that mathematically though? So I know we've been talking about like, oh, normally our speed question is if velocity and acceleration have the same sign, speed is increasing. But in this one, speed of the boat, they're asking, remember, speed of the boat is dx dt. They're just asking, what happens to dx dt as x approaches 0? Because remember, x is the distance from the boat to the dock. So as x gets closer to 0, what's happening to the speed? That's a limit question. That's saying, what is the limit as x approaches 0 of dx dt? Okay, so let's put an equation in for that. So what's the limit as x approaches 0 of right here. dx dt is c times dc dt divided by x. Now, I don't want to have two values for this because c is changing as well, right? So let's rewrite c so that we have this in terms of x. So go back here. X squared plus 144 equals c squared. So c is equal to the square root of x squared plus 144. So I'm going to put that in. The limit as x approaches 0 of the square root of 144 plus x squared times dc dt. Remember, that was fixed. That was 4 divided by x. Use direct substitution. So if I put in 0 here, I get square root of 144, which is 12, times 4 divided by 0. So remember, as x approaches 0, this is going to be 48 divided by a very, very tiny number, which will ultimately approach infinity. So because the limit as the boat gets closer to the dock of the speed of the boat is equal to infinity, it means that the speed is increasing as boat gets closer to the dock. I think that's a pretty tough question. It's been a while since we've had to do limits. And honestly, when I first did this problem, I didn't read it carefully enough. And I have for a few years now done the whole velocity acceleration thing, but that's really not what this question was asking. All right, let's do the next part of this. So part B. Suppose the boat is moving at a constant rate of 4 feet per second. So this time it's what we know is dx dt is 4 feet per second. Again, I'm going to ignore negative signs because they're just saying speed, so we're not worried about the fact that it's a decreasing x value. Determine the speed at which the winch pulls in the rope when there is a total of 13 feet of rope out. So the speed that the winch is pulling in the rope would be the same as the speed at which the rope is decreasing that distance. So find dc dt when c is equal to 13 feet. And remember, that's also, if we need it, when x equals 5 feet. And use the same equation. So x squared plus, my pen is dying, sorry. So x squared, oh, come on now. Maybe my document is dying. No, it's the pen. Hold on. There we go. X squared plus 144 equals c squared. I'm going to use my same equation here. Let's just get it right down to this. It's going to be the same thing. I do some derivatives. I get x dx dt equals c dc dt. All right, so x is 5, dx dt is 4, c is 13. We're solving for dc dt. This is 20 divided by 13, and it would be, again, feet per second. That's dc dt. Okay, a similar question is posed that says, what happens to the speed at which the winch pulls in the rope as the boat gets closer to the dock? So think about this as well. This winch has to start off pulling this boat, and so it's got to pull pretty hard, pretty fast, right? But then once you get pulling, because momentum will help take this boat, you're not going to keep the speed of the winch at the same speed. You're going to have to slow it down, turn it off, let it coast until this thing is pulled all the way up and we can dock it. So it should be that the speed is decreasing. Let's see if we can show that. As the limit, as the boat is getting closer to the dock, so as x approaches 0, of dc dt, what's happening to that? So let's go ahead and put in our equation. Now it's the equation for dc dt. So if you rearrange this a bit, you would get x dx dt over dc dt. And in this scenario, dx dt was, oh wait, sorry, not over dc dt, over c. And in this equation, dx dt was 4. Now, again, I don't want to have two variables here. I want the variable to be c. And if I'm going to do that, then I don't want x to approach 0. I need to think about, like, all right, so if it's x squared plus 144 equals c squared, I want to get rid of the x, so I want to solve for x here. So x is equal to the square root of c squared minus 144. And if x is 0, then what is c? Because I need something to direct substitute into c here. So if x is 0, what would c have to be? You can solve this, or you can just say, oh yeah, c would be 12, because I'd get 144 minus 144 under there. So let's change this to the limit as c approaches 12. It's probably from the right or the left. I don't want to think too hard about that right now. It's probably from the right, I guess. Of instead of x, square root of c squared minus 144 times dx dt, which is 4 over c. Plug 12 into this, and you get 0 times 4 over 12, which is 0. So, yeah, so if the limit as x approaches 0, the boat approaches the dock of dc dt, if that ultimately came out to 0, it means that the speed of the winch is slowing down, approaching 0. That makes sense. You've got to turn the winch off at some point because you don't need it to pull the boat in anymore. Momentum will do the rest. All right. A baseball diamond has the shape of a square with sides 90 feet long. See the figure. A player running from second base to third base at a speed of 25 feet per second is 20 feet from third base. So in this picture, I'm going to keep the labels that somebody drew in. So the distance from home plate to the runner, whether they're at second or anywhere along this line, that's S. We have a right angle here. I'm going to keep this as B, like the base, I guess. I don't know. This is 90. This is fixed. So what do we know? They just told me the player is running at a speed, so I'm going to call that dB dt. This path, the player is running here, so this path has a speed of 25 feet per second. They want me to find the rate at which the player's distance S from home plate is changing. So find ds dt when we're 20 feet from third base. So when B is equal to 20, this little distance here is 20. And what am I going to use? Pythagorean theorem again. So b squared plus 90 squared, won't simplify that, equals s squared. Take the derivative with respect to t, you get 2b dB dt plus 0 equals 2s ds dt. Let's get those 2's out of there and clean it up a bit. This is just like a previous problem then. And we're solving for ds dt, so we know b is 20, dB dt is 25. S is, oh, I haven't found S yet. 20 squared plus 90 squared equals S squared. So whatever square root of 20 squared plus 90 squared is. I should be able to find that, but if I don't have to simplify and it's June 2nd in the afternoon, I'm not going to. All right, so just divide. I could just say, all right, okay, I will do this. 2 times 25 is 50 times 10. So 50 times 10 is 500. There you go. Square root of this, I'm sure this simplifies, but not worried about it. That would be feet per second. That's ds dt. All right, number 37. As a spherical raindrop falls, it reaches a layer of dry air and begins to evaporate at a rate that is proportional to its surface area. And they've given us the surface area formula. Show that the radius of the raindrop decreases at a constant rate. All right, so let's start with this. They did give me this. I don't have specific numbers, but I know that dV dt is proportional to a surface area. That means there's some constant k that I can multiply by the surface area, and that's equal to dV dt. So in other words, dV dt is equal to some constant k times 4 pi r squared. I just have to show that that's true. So what else do we know about the volume formula? So we're talking about volume of a sphere. It's 4/3 pi r cubed. Let's take the derivative with respect to t of both sides. We've done this a time or two in this assignment now. So 4/3 pi times 3 r squared will be 4 pi r squared. And I need a dr dt because I took the derivative of an expression with r, but the derivative was with respect to t. Let's sub in what we have for dV dt. Remember, dV dt, we also know that that's equal to k times 4 pi r squared, which looks awfully familiar. So, yeah, if I solve for dr dt, the 4 pi r squareds cancel, and I just get k is equal to dr dt. So this means that dr dt is changing. K is probably negative if it's decreasing, changing at a constant rate, which is k. All right, last problem. A balloon rises at a rate of 4 meters per second from a point on the ground 50 meters from an observer. So let's get that picture going. Here's my observer. Here's my balloon. 50 feet. This balloon is rising at a rate, I'm going to call this dy dt, 4 meters per second. Find the rate of change of the angle of elevation. Ooh, we should know this from pre-calc. Angle of elevation is from the ground looking up to the balloon, from the observer when the balloon is 50 meters above the ground. So we know, I'm calling it y, so dy dt is equal to 4 meters per second. They are asking me to find, what was it? Oh, angle of elevation, d theta dt, when the balloon is 50 feet from the ground. So when y equals 50. And remember, x equals 50 is fixed. All right, and so if theta is involved, I need to use a trig equation. I could find the third side. Maybe I'll need to at some point, but I have opposite and adjacent. So I'm going to use tangent theta equals y over 50. And then when I take the derivative with respect to t, the derivative of tangent is secant squared theta d theta dt. The derivative of y over 50 is 1 over 50 dy dt. And again, remember, when trig is involved, for all of these d theta dt problems, you should never be finding the angle itself. We don't need that to figure out what secant squared is. Remember, we have this right triangle here where we have both legs. They're both 50. That should remind you of a 45, 45, 90 triangle. So, okay, I do know that theta is 45, but I don't actually need that, right? I could just say, oh, this is the hypotenuse is the leg times radical 2. Or these can be reduced, whatever. 1, 1, radical 2. Because secant theta then is hypotenuse over adjacent. It's radical 2. So this is radical 2 squared, which is just 2, times d theta dt is equal to 1/50th times dy dt. That was given to me as 4 in the problem. Now there's just stuff to clean up. 4 over 50 is 2 over 25. And then this, remember, this is like 2 times d theta dt, so divided by 2. So I get 1 over 25 for d theta dt. And what is the measure for that? It's always radians per second in this problem. The time can change, but theta is measured in radians. Okay, I know that was a very long assignment. Hopefully, we got some of that done in class. Feel free to come to office hours to finish it up. And of course, if you didn't get finished with it in one shot, just make sure that you're working on this prior to our quiz or test.